Okay, good morning. Thanks everyone for coming this early in the morning. I know it's only 8:30, but to consider that it's actually 2 o'clock in the morning in Redmond, it's even earlier. So my name is Wenming Yi. I'm a technical evangelist over at Redmond, Washington, and I work for the Azure evangelism team. So we have a team of I think it's 13, maybe 12 people. That covers from websites to virtual machines, IaaS, to HPC and big data and ASP.NET, a lot of the Azure technologies. So my primary responsibility is on big data and HPC. So anything that involves more than one machine, I'm covering. Simply because of the background that I have, which is working with large data sets, working with large simulations in the past. So today we have a very interesting session, mostly on scenarios of developing big data applications. So it's really meant to help introduce you to what people are doing with big data. Aside from the big buzzwords that you guys have been hearing about, and some of you might be tired of hearing about the word big data, so I'm going to teach you a few new buzzwords, such as machine learning and collective intelligence. And we'll go through examples instead of just talking about them as well. So the first thing I would like to do is to help everyone understand the characteristics of big data. From my perspective, this is not the general industry perception, but from what I've seen. And the difficult part about defining big data is that it is a new industry, and it's really hard to define what exactly big data is. But I'll give you 6 different perspectives from current vendors and tools so that you have a broader idea of what it really means without any biases from any one of these industries. And the second piece is just getting started with some of the big data tools. And most of these tools are open source, which includes Hadoop that we'll talk about, which is actually the elephant that you saw earlier. So that's the elephant. And by the way, this morning I discovered that there's actually a laser point on these things. I've been working, doing presentations for about 4 years and never realized there's actually a laser point. I'm actually going to use that. So there's your big elephant. I actually made that. It's really amazing what you can do with PowerPoint by simply selecting a little template for it. So we're going to look at how you use some of these open source tools. And some of them are relatively primitive, but the interesting thing is to see what people are using them for. And they are for real. And this is what the industry is generally using now, essentially using large clustered machines to be able to deal with large data sets. And also recognizing appropriate scenarios for big data. So not every scenario is actually appropriate for big data. So there might be things that you could simply do on your desktop and people didn't realize. So just because you have big data tools doesn't mean that you should apply big data tools to every problem that you have. I also have 3 bullet points for agenda. One is that I want to define them from the different perspectives and also the components and challenges, some of the issues that we run into that are fairly real. And finally, I'll go through 4 different scenarios. The first one is to look at how you can analyze log files using the tools, some of the primitive tools that we have from the Hadoop ecosystem. We'll do a simple example. All of my samples are actually stored on a GitHub, so you can just go to that URL and just play with them right away. And the second piece is the second scenario that I'm going to go through is the analyzing some text and showing you how people use things like matrices to understand, to map mathematical equations to actual data set to get derived meanings out of them. So the example I'm going to give is running a SVD algorithm over a piece of text and show you that using matrices, you can actually relate words and tell how much the words are related. And the third example I'm going to give is something called that came out of the Mahout algorithm collection of Hadoop. So essentially show you how to run a recommendation engine. So most of you probably have used Amazon or have listened to Spotify and Pandora, most of you probably. So I'll show you how that recommendation system actually works. And finally, there's analytics that I want to show you how to look at Twitter data, so that that might be interesting. Looks like there's a few more people that showed up. Great, thanks for coming. So, big data. People have been showing these slides for quite a bit by now. It's really simply showing you the amount of data that exists today and also what you're going to see in 2015. So it's going to quadruple. And what it really means is that we're not going to process all of that data. We're going to process some of it. And it's just simply showing you the sheer volume that we have to deal with today. So here is something that I thought of when I think about big data, which is the original story is the 6 blind men, which each of them are very honest. But the problem is that they could only see a small part of what big data actually represents. So this is really a very good resemblance of the current industry of the very new industry of big data, because people are still struggling to define what it means to be big data. So I will actually try to define it from 6 different perspectives. One is from the relational database. Relational databases have been dealing with data all along for the last 20, 30 years. It's based on set theories from mathematics, and it has really worked well for us. It doesn't mean that you have to change that today. If you still have important data, such as your social security numbers, you wouldn't want to store that in a Hadoop system, probably not. But relational databases still work. But the problem with some of our, at least some of my friends that are from the relational database background, one of my friends works for a really large online system. So so I asked him once, just for fun, is that how do you like working for a Web 2.0 company? So they use Ruby, and they also use MongoDB and also Hadoop. And I said, how do you feel like transitioning from a DBA that you've been working for on mobile licensing companies, very secure databases? He says, one thing I really didn't understand is that why is it that we can't use referential constraint in big data? Big data people don't understand that piece. So he is right and wrong at the same time. The reason is because for what he did before in terms of databases were perfect because it's secure and it's your data is very safe. But on the other hand, he didn't realize that the data for the new company he works for is actually not really all that important. It's not as important as your social security numbers. So some of them are simply things that users posted, or maybe information that's good for 3 months and then you just simply throw away, right? So it's not as important anymore. And the second piece is actually from HPC vendors. I see, how many of you actually deal with really large cluster hardware or have dealt with? Oh, I see a few. So the HPC vendors are making a huge amount of profits right now on big data. The reason is because they have been building really large cluster to do scientific computation for many years. So they really know how to build these systems. So the world's largest systems are up to millions of cores, including GPUs. So essentially, these are really large cluster systems. So I think the largest Hadoop system for big data is actually not nearly as big at this point. So the difference between an HPC cluster and a big data cluster is that you're maximizing the CPU or the computational power for high performance computing. And while for the big data Hadoop simulations, you really want a lot of spindles, or maybe you want some SSDs in your configuration, but you don't necessarily care so much about the CPU. But at the end of the day, you're building a really large cluster. So essentially trying to solve really large problems with divide and conquer. And I have a really good examples here, right here. So here's a cluster. We have 5 water bottles. So if you want to add additional nodes, you simply add more water bottles because it's cheap and it's scalable. So this is how a cluster works. And then search engines. So Hadoop was actually invented for a search engine called Notch. So Google actually invented MapReduce. So it's really a paradigm where you have 2 real simple operations. One is map, essentially taking tasks and farm it out to each individual nodes that you have on a cluster. So I have the simplest example here, right? So each of these water bottles will be working on one item, right? So the reduce operation is that you're aggregating information after you have processed them on these individual nodes. So that's the map reduce operation. It's a very simple paradigm, but it's very powerful because it summarizes what a large cluster can do, which is to divide work into smaller pieces and then aggregate them back together. And another very important piece is programming environment and programming languages. So one of the most popular big data language is actually R. The reason is because it has a lot of statistics packages built in. And big data is about machine learning. It's about trying to figure out relationships within your data set. And sometimes we are trying to find known problems. And also sometimes we may have things that we don't even know that we're looking for. So it's really about asking the right type of questions through statistics. And Python is a great data language, which I actually have a demo for today. People use Python. So a lot of my friends over at Tengen, which is the MongoDB folks, so they have more and more people using Python to interoperate against their MongoDB cluster. It's becoming a very important language and a very important part of big data. And also, algorithms and machine learnings are probably the most important piece, in my opinion, for big data. The reason is because you really need very optimized algorithms when you deal with really large data sets. So I'll give you a very simple example. The other day, I was trying to process about 48 million records on my cluster. And each of these records had to do 4 billion operations, additional operations in a MapReduced operation. So what happened was I actually wrote the wrong algorithm. I was trying to do a search linearly inside a 4 billion record. So of course, you know what happened. It took about 14 days to finish what I needed to do. So I modified the algorithm slightly, which did a binary search, simply a tree search. You said, OK, if it's larger, so I actually divided it in half. That took just a few minutes to finish the whole data set. As you can see, if you didn't have the right algorithm, you end up having lots of problems. And also new algorithms that are coming online, because now that you're operating on so much data that they don't necessarily fit in traditional memory, which is what we are used to program against. So you program against memory, that's really easy. But when you program stuff against hard drives, which is much larger data set, your performance and your algorithm would all have to change based on the characteristics of your storage. And finally, social data. I think that's actually another really important piece, which is how big data became popular. Big data became popular is because Web 2.0 companies suddenly found a new way of extracting information from the low-density information that they collect, such as log files. So they collect a lot of log files that actually contain behavioral information of people. So it's really what we call the collective intelligence, what people did and what people actually liked. So Amazon collects a lot of that data, so they make recommendations to you. We actually have an example of that today. And of course, there's a lot more perspectives to what big data is, but I think those are the most important ones about big data. And if you guys have more ideas of what it is, if I'm missing anything, feel free to send me a tweet, and I will add that to my deck later. So the other interesting thing is that people in the industry have designed something called the 4 V's of big data. The volume, you already saw that. Everybody understands there's a lot of data. But the other ones are really less known. The one that, so we're going to go clockwise here. So the variety of data, if you actually simply go to, I think it's opendata.gov, the US government publishes so much data. So the other day I was trying to find out which data centers they're closing. Apparently the Obama administration, in order to save costs and move things onto the cloud, they're closing down, I think it's 400 or 800 data centers. That list is actually on opendata.gov. So you can find a lot of these information. It could be really detailed information. And you can find all kinds of information on the web. So this is one of the reasons that big data is suddenly becoming a very popular topic, is the availability of data. But of course, there are challenges with the availability of data, because sometimes if you don't have good data, you won't be able to do that. But now that a lot of places are starting to provide more and more data on the internet publicly that you would have access to either as a paid service or for free. So you suddenly can do a lot more. And the velocity of big data, right? So the velocity is really about how fast data moves, how much data you actually get in a day. So Twitter is a perfect example. Some of my colleagues actually analyze Twitter data over at Bing. I actually had a former boss that works for a company called GNIP. So they actually have a full access to the entire data pipe as well. Every day you have almost 200 million tweets. So this is fairly large amounts of data. Also think about the velocity of your accruing data every day at Facebook. It's probably more, even more, because people would add photos. There are people add other interesting things. So we actually have an example of analyzing tweet data today, showing you how to take that data, transform it into Hive, and run interesting queries over it. And finally, variability. That's actually one of the ones that's relatively difficult to explain. Variability actually means the differences of data, the meanings of data, depending on different context. We actually do have an example of that, showing you words have different meanings under different contexts. Another perfect example is Jeopardy. So how many of you know about the game Jeopardy in the US? So, oh, great, everybody, wow. So Jeopardy is different depending on the context. Recently, I think IBM, there was an IBM supercomputer that actually won a game, right? So they won a game, but figuring out what the context is relatively difficult. And I'll try to suggest some of the reading materials you can do to look into that area, because I'm actually have a little bit background in that natural language processing prospect. And of course, as these new technologies come in and as things become cheaper, as clustering machines become cheaper, we would be able to use this for a lot more things because of the availability of data, availability of cheap clustering, and also availability of the cloud, right? So the ability to do analytics on really large data sets suddenly becomes cheaper. So here are some of the interesting scenarios you can do, just as a general idea of what you might be able to do with it, right? So, so one of the things that I work on quite a bit is risk analysis for really large portfolios, and depending on conditions, and also not just simply market conditions, but also on other things like Twitter data. I have a very simple demo that I'm building currently, which uses a very simple Viterbi algorithm. So when the market is actually not doing anything, you can figure out in real time how much risk there is, and also based on Twitter feed. It's just simply a demo, but suddenly the fact that I can build demos like that is really powerful. Of course, if you are really good at it, you can probably make money of it. So lots of things that you can actually do. So here are 5 elements. Actually, see the first 4 being the factor that doesn't involve the human beings, the data. data is extremely important. You cannot do big data without data. And that's probably one of the most difficult thing. So I try to do I try to do a lot of interesting big data demos, but sometimes you just simply can't find the data. It's really difficult to find good data. And then I think I had multiple conversations with multiple people about data sets. Either people own it, or people don't want to give it up, or, oh, you can't have it. So that becomes really quite difficult. But what I found that there's a lot of data sets that are available on the internet. So today we actually show an example of a million song database. So there are free stuff out there, but at the same time, go look around on your hard drives, find some data, and put it on the internet, because it may have a lot of values to it. So just because the big data industry is very hungry for good data. And good data is really hard to come by. So if you have data, there's a business opportunity for you. Making those data clean and make them online is a huge business. So second piece, hardware. HPC and big data are all about clustering, so making them cheap. Hardware, when they say commodity hardware, they don't actually mean your $200 laptops or your little handheld phone devices. They actually mean that hardware that are cheaper than the Superdome and all those really expensive database hardwares. So some of the hardware that Yahoo is using for big data involves 12 spindles. I mean, those are not commodity hardware that you have around your basement, do you? Probably not, right? So those are a commodity in the sense that you can buy them. You can buy them relatively cheap, but not, for your 10-year-old PCs. The third piece is that tools for solving time-space complexity problems. So we really need these large-scale data processing tools that are ready to go, and also the ability to apply them in a map-reduced fashion. So tools such as R and Python, they work by themselves, but the industry is really working very hard to make these tools work well and integrate well in a clustered fashion, meaning having them work on really large machines and large systems. And finally, scaling. Scaling is absolutely the most important piece. If your cluster don't scale, then you're not really able to solve really large problems. So the idea of Hadoop is to use these commodity machines, and you simply add nodes to them. So if I run out of storage in the distributed file system, I just add another bottle. So here's another bottle of water to my water bottle cluster here. And you want them cheap. And it's not simply adding a big RAID system. It's really about that plastic bottle. And it's cheap. You're not making another really large system. And that way you can really scale out. So I think that's really the what I call the man-machine moment thing. So and finally, the most important piece is your data scientist. You can't do big data without the knowledge. And I think there is a huge difference between really good data scientists and with people who are just starting. So I'm a little biased because I came from the physics background. I really think that world's best data scientists are from science background. Or anything that says science, there's say data scientist or data science or computer science. Anything that says science, that's not really science, right? So you want people who have background in biology, background in physics, chemistry, because they deal with data. They have that intuition for data sets. And if you look around, some of the most successful startups are started by physicists because they deal with that. They do simulations, and they actually understand the mathematics behind it. And of course, I'm leaving out applied math folks. And the other thing is just, the curiosity, being very persistent and understanding that dealing with big data means you need a lot of patience because a lot of waiting that happens. We're going to do a lot of waiting today. I got lots of examples that runs for a while. So finally, I want to talk about Hadoop on Windows Azure. So the story is that we announced that we're going to support Hadoop at PAS of last year. I think it was October. So now there's actually some private CTP that we're providing on Windows Azure, and we also have an on-premise version that we're integrating with AD, Active Directory, and also make sure that they work properly on the Windows operating system. And also, we are working around that distributed system of Hadoop and adding additional values to it, such as allowing you to connect to our BI technologies, such as, I don't know, Excel and Power Pivot. So things like that. So I want to really go into more examples and scenarios because I think that I had a colleague, Matt Winkler, who gave a talk earlier yesterday, I believe. So if you want to look at more about what Microsoft is doing, you might want to take a look at that session. So I'm going to go through some of these real quick because most of you probably already understood what big data does and how the architecture works. So I'm going to make it really simple. Big data means that you want divide and conquer to solve really large problems. You're taking a really large problem, you're trying to divide it into smaller problems. So if I have lots of files, I divide it up and put it on lots of servers. So there you go. So it's using cheap commodity files, boxes, and you just simply shovel some files on it. And then there's a Hadoop file system that actually keeps track of it. And also, this is the MapReduce operation, which I talked about earlier. This is probably the simplest thing you could ever think of, which is 2 operations. There's nothing difficult about it. You're mapping some work onto each of the nodes, and then you're collecting information back. The simplest operations. I call them the assembly line or assembly instructions of big data, which is everything else builds on top of it. As you can see, it's really simple. You run this piece of code on each one of these machines. And of course, a program involves millions and trillions of instructions. So is a real MapReduce program. It includes many MapReduce steps if you are running a really big one. And if you're using some of the higher level languages, such as Hive, which is a SQL-like language, which you process large data sets, it will decompose these things into many, many steps. And it will keep track of all it for you. That's the power of Hadoop, which is it's a distributed system that's transparent to you as a user. So here's the architecture, very simple. You have underlying file system, and you have a job task manager, which maps the proper operation onto each node. Because Hadoop knows where the files are in your large file system. And finally, there's the ecosystem. I'll only mention Hive because we're going to do a lot of examples in that. It's very much a SQL-like language, which is what a lot of people running SQL are familiar with. You can simply run that, and you don't have to worry about what's actually doing underneath, which is hundreds of MapReduce operations underneath. So let's go to my first scenario, which is dealing with data exhaust. By data exhaust, I mean log files and things that you don't normally look at so much before. But now you have the capacity and capability of a cluster to look at it. So here is a fairly simple diagram, your e-commerce data warehousing product, which is a lot of your good data, which is the stuff that goes from database. You keep them in there. And then the logs, maybe I'll keep some of it. Maybe I'll delete some of it. I do some ETL. And most of it I'll probably delete because I don't have the capacity of storing them, right? So now since hardware becomes cheaper and you have a Hadoop system, we could actually keep all of them just for fun, just because we can afford it. That's more of like it, right? The data might become valuable later because there are unknown unknowns in the world that we don't even know whether the data set is available and valuable or not until we actually process them. Maybe we don't even have the capability of processing it today. Maybe 2 months down the road, someone else we hired could actually look at it. So this is the reason, and the interesting thing about it. So let's actually look at my first demo. That's enough talking for one thing. So look, I'll switch over to my demo machine here. I don't think I typed in my password, right? Let me hold on one second. There we go. Thank you. All right, so the first thing I want to introduce you to is the Hadoop on Azure portal. So as you can see, I'm already logged into my portal. You can do a lot of interesting things with it. Unfortunately, it's still in a private CTP, which means you don't have access to it, and I apologize for that. But if you do actually sign up, they might clear your queue after maybe a couple of days. Actually, I mean a couple of weeks. So Dennis here, have you gotten an account yet? Okay, so how long did that take you? Well, he's lucky, so 10 minutes. He works for Microsoft, so don't believe him. So it might take a little longer. So if you look at this, it's very much a very simple portal, right? So you have interactive console, and you can manage your cluster. You can do disaster recovery, and you can go to the data market, import some data, which I have a lot of demos for. I'm not going to go through that today. And you can set up an ASV, which is blob storage on Azure. So you enter your storage account and also your storage key. It's really simple. You go to portal and get that. The second thing is that we have an interactive console and also remote desktop for that. And there's some job histories. As you can see, I run a lot of jobs just for fun, right? So let me go to interactive console. So this is very much like the command line on your Unix box. So I love Unix boxes. So if I do ls, you can see there are some files there. You can do a cat of some files. But what we want to show you is that I actually have some log files on the service logs. So I have some log files that I would say collected or reprocessed from certain online services. And what this has is not really a weblog, but more of a IP address plus the what country connections are coming into from. So I can do a pound. As you can see, it's really Unix-like because Hadoop really runs on a Unix box, right? So I can do a cat and then samples.log. I think it should work. So you can see that all the files show up as very somewhat structured, right? But normally, what would you do with a database? You probably import that into a database. It'll take a little while, right? So what you can do with Hadoop is you can, or Hive, which is a higher level language, you can create a table. You say, I want to superimpose a structure on this data, but I'm not moving that data. I'm keeping the data as is, and I'm not doing any type of checking. So there's something called check on read and check on write. So for normal traditional databases, you do a check on write, meaning that you actually, when you try to get data into the database, you make sure that integrity is good when you import it into your database. But here, I don't check anything. I only check when you do a first read. So simply saying, hey, there's some data there. Let me put some structure on it. Let me actually just run against that data set without moving it or changing it or touching it, because I could have lots of data, gigabytes and gigabytes of it. So here's a really simple demo. I want to actually show you the code real quick. So here's how I superimpose a structure on top of Hive by simply saying create external table service log. As you can see, I can specify a location and also note the external, meaning that don't touch it. Don't import it into the Hive directories. Don't do anything to it, which is great because that's what I want. I want to keep the data set right there in my Hive table. So here is here's the actual command. So I'm just going to go run that. I think it should run fine. So one of the characteristics of big data or these really large systems is that it's doing a lot of MapReduce underneath, and has a really high cost of starting up. So anything you do, it will take a few minutes. Let's say if I want to process 1 million records and 10 records, they'll both take you about 2 minutes. So that's the interesting thing about it. So here it took about 4 seconds for me to superimpose that and create a table. And say, now I actually want to query against it. So the query, so just want to make sure that everybody can see this. So I can do a select from that table, right? So I can just simply say a select from that table. That's very similar to what your MySQL or SQL data language looks like. So I'm going to go run that and evaluate. But now what I'm going to do is I'm going to terminal service into the actual machines. I have 4 nodes. with a head node, of course. I have a head node, and I have 4 worker nodes, 4 of these actually working on it. So if I just click on the system, and let me see. So just click on the Hadoop MapReduce, and you can see that I just ran a job, and if I refresh it, hopefully it will actually, let's see, did it actually do anything? So it would actually run a little query. I already finished, that's the reason. So I did a select star from service. As you can see, now I can operate on it without actually changing where the data is or modifying what the data set looks like. So this is just simply saying, OK, what does the data look like? So at the end, I actually have a country code. So what I want to do now is to actually show you how to query the data set from a point where I am grouping that by how many countries, the top countries that actually visits my site. So this is the query that, that I used. So create a table, and as you can see, it's really simple. And also, it looks just like a normal SQL query, right? So, so this thing is going to run for about 2 minutes. So what instead I'm going to do is I'm going to go over to the JavaScript console, which is something that we really did a great job on, our engineering team, not me. If I actually look at some of the data set that I already have, as you can see, I'm selecting all this data into a Hive table. And it says, there's a little table. I have one pre-calculated. So if I do a ls/-hive, this is where Hive keeps all its things. So the interesting thing is that the file that I have that's on blob storage, that is kept external. I'm not doing anything with it. But when I create a table, it normally keeps it in the warehouse. As you can see, I have a couple of tables here. One of them is the top country, right? So I'm going to say top country. It even does file completion when you do a tab, which is really nice. So I'm going to say cat, all of that. This is the query that I ran earlier, which has the results. So I'm going to do a cat star. As you can see, it has 2 columns. You can barely see it because it's kind of squished together, and I'll explain why. So you have a United States, and then there's a number behind it, right? So this is Hive, which means they delimitate their tables by control characters, meaning that the first character, which is Control A, by the way, is delimiting it. But when you do a cat, it doesn't show up. So how do you parse that? So there we have a command called parse Hive to actually be able to parse that data set. So let me actually go back to the little command I had. So what I want to do is I can simply read from that file. As you saw earlier, I showed you where I put it, right? So, so I'm going to read that in. So I did a file read. So it read the file, and then I need to parse that file, right? So I'm going to parse that file by using the command called parse Hive. So this is once you parsed it, you actually set a little schema for it. The reason is because it doesn't really know this is an integer, right? So since this is JavaScript, so you actually said, okay, I want 2 columns. The first one is the country code, and the other one is simply the how many counts we had. And then we can do all kinds of plotting plots right there in the JavaScript console. This is all done by Microsoft, and we're contributing that to back to the Apache Foundation for what it can do here. So I can do a graph.bar, and as you can see, it's really easy. And I can do, of course, I love my pie charts, right? So as you can see, the next localization for my application should probably be, I can't really see it. I think it's Brazil, so that would be Portuguese, right? So that would be something that you suddenly have a lot more confidence just by simply looking through your data very quickly for a few minutes, and you're done. Of course, you can use Excel to connect to it. We have provided an ODBC driver, and I think Matt showed that yesterday, so I'm not going to show that. Simply what you do is you connect to your cluster and do a plot. So it's pretty straightforward. So this is my first demo, and let's actually take a look to see if my query finished. So I can go to Hive, and actually it did. It took about 202 seconds to process about, I think it's 48 million records that I have. So it's not too bad when you consider that the machines that I have are actually really small Azure machines. They're 2 cores each, so they're really small. And also, you're pulling data actually from the data storage. So normally, when you do, so I consider this audience as a bit more advanced. So let me explain. Normally, in a Hive operation or Hadoop operations, you have everything stored in a HDFS, which is local file system, but clustered, transparent to you as a user. But here, I'm actually pulling data out of the Hive, out of the blob storage, which means each of these nodes are actually going back to the blob storage and accessing that to pull the data out. So the nice thing is that it's still faster because I have 5 machines doing the work. But the other thing is that it's not really the normal paradigm of Hadoop, which is keeping everything on a local file system and put them together. But the interesting thing is that it works, and I get to keep my data where it is, right? So let me actually switch back to slides. We have a lot more demos to do today. So this is the other piece that I really want to show you is that given that we have logs are from human behaviors usually, but there's a lot more logs that are coming up from Internet of Things, meaning that your devices that are just spewing out data without you knowing. There's also sensor data all around. There's so many people building sensor networks and also new kind of sensors, tying them to cell phones and doing interesting things. It's just a tremendous amount of data that we can collect about our environment, not just simply about ourselves. So here's an example that I want to show you. Those are the pictures I actually took from last year's American Geophysics Society, which I'm a member of. And here is a really nice little sensor. Now I learned how to use my laser pointer here. So this device, you put in a river down to like, I don't know, a mile, not a mile, maybe a few hundred meters, and actually be able to measure a lot about the water that's in the river. Well, the water quality or the salinity, they call it, how much salt you get. And here's a weather balloon from NASA. So you can actually take something and go up to 5-10 miles and measure the upper atmosphere. And here is a really cool, futuristic-looking device. Anybody guess what it is? Anybody? Anybody from atmospherical science? No? Okay, so what this does, it actually measures how much particles there are in the air, water particles, using a laser. So it's really cool. You can actually take this device and either put it on an airplane or actually put it really high up to the atmosphere. Here's another really cool project that Microsoft did, which is collecting data above the cloud. So they actually took this little weather balloon to 10 miles using GSM data to transmit data back. So these are our friends from Southampton University in the UK, where they actually took a Windows phone, actually transmitted sensor data through the GSM network at 10 miles up. I think it's 60,000 feet. That's actually 11 miles, right? 11, 12 miles. That's, in your terms, it's more like 30 kilometers, a bit more, maybe 30 kilometers or so. That's actually pretty high. And this is actually being launched, and then there's the balloon, and then it actually came back down to Earth. So as you can see, there's a lot of creative things you can do, and these devices are not expensive to build. If you go rent a plane, that's $100,000 every time you go rent it. But here, this thing costs just, I would say, a few $1,000s. That's it. $600? Oh, great. Well, we have someone to talk about it here. Well, excellent. Well, we'll have to give you a round of applause there. Okay, so $600. Now you can build a sensor and send it to 15 miles up. I don't know what kind of ideas I'm getting out there, but I think I'm building one after this. So the second scenario, I really want to kind of explain this really well because this is actually a very important piece of big data. Understanding how people actually do the computation behind scenes, the algorithms, and the data structures, how you map documents and unstructured data to mathematical representation and do the computation. So the matrix has always been around. We do use it for HPC and other type of anything that you want to simulate in a physical condition. You put them into a matrix or finite element representation, and you do that. This has been around for, I would say, 10 years, 20 years, 30, 40 years. It's been around since computer has been around, really doing large computation. So the basic idea, the meaning of a document is determined by the words that it appears in. And if you reverse that, the meaning of words is determined by the document which it appears in. So as you can see, there's a mathematical relationship there. So let me give you an example real quick. So if I do latex semantic analysis on words that are not really the same, you suddenly see that I have a relation. We'll actually do a very good match. But if you do words that are not related, you're simply doing a word search, you don't do anything. You won't be able to find anything. That's why interesting algorithms actually gets you ahead much more. So this is not new technology. This is actually technology that has been around for 10 years. I actually worked on that at my university. And this patent actually got bought by something called ETS, which is the people that put out TOEFL and GRE and those tests. So they use them for grading essays. So the accuracy is at 81%, as to human being 85%. So they really do work well. And they're used in all kinds of new, the technology has really advanced much more at this point. So here's some interesting things that you can do. What you can do is you can take a document and you do some word count, which is Hadoop is really good at. You take lots of documents and you do word counts on them. And then the next thing you do is you create a matrix. But that matrix is not really useful. But what's interesting is that you create a vector that's a word vector. As you can see, human appears in all these documents. And the document has all these words in it. As you can see, there's a relationship that you can map out in the matrix. This is how a lot of things work. For example, similarity matrices, what you purchased against another person, those are all very much, you can do in that. So I want to explain a very simple concept called the single value decomposition. So it's just simply a mathematical decomposition of a really large matrix. You either know it or you don't really need to understand it too well. The point is that I'm taking this really large matrix and dividing it up and transforming it by turning the radio knob. This is what the data scientists actually do. I create a new matrix by taking two eigenvalues from the matrix and create a new one. And suddenly I have this matrix which I can query against and figure out how the words are actually related or not. And this is another interesting thing, is determining similarities between different aspects. So using cosines and dot products and Euclidean distances, simply saying how far these points are in a higher dimension allows you to be able to tell some interesting things about your users and your products and all kinds of fun things. And this is what people do. So I'm going to run a really simple demo for you using our not really well-known but really powerful tool called the Visual Studio Python tools. I think it's called tools for Python tools for Visual Studio, I believe. So let me switch over real quick. And here is the, where's my Python? There you go. There it goes. So what I want to do is just paste something really simple. Create a new project. So File, New Project, New Project. You can see that Python is a first-class citizen now in Visual Studios. This is not the .NET Python. This is just simply the regular Python, right? It's just Python that people use. That's native on each platform. So the second thing I want to do is I want to actually show you a very, I actually created the matrix inside Python and show you how easy it is to actually run the query. I'm going to copy this little program, which you can see using high-level languages, there's really not much to do for data scientists, and this is what they generally do. So I'm going to save this file, and I forgot to do that last time. I'm going to actually go to debug and execute that program. Real quick. As you can see, Control 4, I believe. How do I do zoom it? Let me see, zoom it. Let's see, there's my zoom it. Run it. Oh, now I can actually zoom, right? So as you can see, the relationship between these words, within our context, relationship between human and user is really good. But on the other hand, relationship between human and miner is not so much, because if you look at the original sentences, it's very different. So let me show you the original matrix so you kind of understand what I did here. So if I go to demo 2 and I show you the original sentence, as you can see, miner didn't actually show up. As it didn't actually mean that, right? So you can see that human. Oh, slow down 1 second. Where's my? I want to point out that. Yeah, actually, there are 2 systems here. Apologize, I'm going to go to one of these. So as you can see, there's some very interesting things here. So this is really a very good example of how you can use mathematical representations that simply you do some minor processing and be able to query against some interesting information about it. So the other piece I want to do is actually look at tree and graphs. So tree, there's two meanings to a tree. Tree is a representation of a mathematical format, right? So there's your computer science tree, and then there's the tree, right? So I want to take a look at how different tree versus, tree versus, what is it called, a graph is. So it's really line number 9 versus 10. So you can see there's the word tree and graph are, column number 9 and 10. And I can, show you. There it is. So there's, can you guys actually see this well? Okay, so there you go. So there's graph and miner. We're going to do a little computation on that just interactively. So I would come back to here and copy the second example of this. Oh, let's see. That was the first one. I'm going to go to my second demo and copy that one. So as you can see, I'm simply doing a dot product on them and finding out the actually it's really more of a cosine. So let me run that real quick and press enter. As you can see, it's very much related, right? So graph and tree, within this context, once again, within this context, it's very similar. So the idea is that matrices and linear algebra is applied across the board, and new algorithms are being invented for MapReduce operations. Okay, so let me switch back here. So I hope this is interesting so far. Okay, great, thank you. So the other things you can do is you can actually do image analysis. Really cool. I actually tried to do some of that. It turns out to be, my algorithm turns out to be a little slow. So now I'm looking at OpenCV to recognize certain objects within your images. So there's a lot of things you can do. MapReduce is just a simple mechanism for distributing out the workload, but the algorithms which you apply. For example, if I want to find stop signs inside all the map data that we have, right? So that would be a very interesting problem. So what kind of heuristics do you apply to? There's a lot of interesting things you can do. It's not just simply doing word count and that sort of things. There's just whatever you can think of and do it in a larger scale. So credit card companies uses this quite a bit, and they've been doing this for a while. In fact, I was just talking to a credit card company, and they are using Hadoop. It's one of the major credit card companies. I'm sorry, the credit bureau, right? Credit bureau is actually using that. They're based in the UK. Other possibilities, you can do a lot of interesting things. Basically, predicting holiday retail information. This is really useful because we know that in holidays, suddenly searches for digital cameras, searches for certain products suddenly just goes exponential. And then it just taps off during the rest of the season. And apparently, people really search the word vodka on Saturdays. And Sunday, they search for hangover. Scenario number 3. I want to go through this relatively quickly. We have about 20 minutes to go. So this is a recommendation engine that's built into Mahout. Mahout means elephant driver. Is that driver, herder in Indian? Oh, okay. Maybe Hindu, I'm sorry. What we're doing is that it's really simple. So if you look at user number 1 and user number 2, those two guys are really very similar as opposed to user number 1 and number 3. So let's just say user number 1 really likes book number 1, number A, and user number 1 does not like B and C. User number 2 does not like B and C, but he likes the book number A. So what book would you recommend to the first user? Probably the one that the second user has additional data for, right? So that you would do that. And user number 3, we just say, hey, we don't know what you like, but we might recommend something to you at a lower probability or lower certainty. So what you do here is you run a similarity matrix and try to figure out what these guys are doing. So what I'm going to do is simply show you how easy it is to use existing software algorithms that comes with the Hadoop ecosystem. So that's why one of the reasons that Hadoop is so popular is that there's stuff that already exists. There's a user community. And Microsoft really loves to have this user community talk to each other, be able to use what already exists instead of us doing more things for you, but you can already take advantage of things that already exist. So let me actually show you how that works. The first thing I did is actually downloaded the Million Sound database. There you go. Oh, wait. So I'm actually supposed to show you that I'm doing this demo, and that there's additional algorithm. We'll talk about that later, what they're good for. So I actually have a demo here. That's demo number 3. That is just simply a Mahout training data set. So as you can see, I do have some big data here. This is not going to be opened by Word, so I'm actually going to use more. So one of the things that's cool about Windows is you can simply type CMD in there, and it takes you right to that directory. So probably some of you know about this feature, and some of you don't, right? So if I say more, let's see, what files do I have here? So if I say more, training set, this is a 3 gig file, right? So what it contains, I'm going to do my trick on zooming in again. What it contains is, the first column is number of users, the user ID. It's just one guy. And on the second column is this number of songs that he's looked at and how many downloads on the third column. It's simply saying a triplet, which is user, song, how many times you've downloaded it, right? So this is a data set. Let's just say you aggregated from your, if you're an online video company or you're Spotify. So they collect that information, right? So we have that available. You can download that for free. And I provide all the code for you to play with this in my GitHub account. So the next thing you do is you actually want to transform that a little bit. I wrote a Python script, but you don't really need to do that. I already have code on that you can just use. So instead what happened is I actually transformed it to a much simpler form. Can you guys all see it as well? Okay, great. So instead of really long numbers, I'm just transforming it into this. This feeds into Mahout. And the next thing you do is I want you to take a look at the output first because it takes 20 minutes to run. So here's the output, which is what it looks like. So for user number 1, after I run through this big simulation, it will show you, okay, so song number 95, I'm within 4.7 certainty, saying I'm pretty sure that you like that song really well. You might like that song really well. And for user number 2, we're not really sure. We don't, you probably don't have enough information, so we don't know. So as you can see, for user number 6 there, we're really sure about what you like, what you don't like. So it might actually run the simulation for you. So the first thing you do is you can upload all these files using fsput and fsget to upload your files. So I can go to JavaScript console and take a look at let's see, take a look at what I have already uploaded. So I do ls. So if I do ls input, my input directory already have my files uploaded. So if I want to upload additional files, I can just say fs.put. And then you can just browse a file and put that file there. So I already put those files there. I'm not going to do anything more to it. So if I do a _ls, again, you see that I have a temporary directory and an output directory. So if you do output, I'm just going to do cat everything inside the output directory, star. As you can see, that's the results that I got, right? But there are intermediate steps which it's actually doing, which is the similarity matrices and all those things that it computes in the middle of it. So that's in the temp directory. Actually, I'm going to do ls, temp. So there's a lot of interesting things there. As you can see, it does a lot of MapReduce operations. And let me make it a little bigger so that you understand what actually happens behind the scenes. Not necessarily this particular implementation, but how some of these things work, just give you a flavor of it. So as you can see that there's an item user matrix, so there's a similarity matrix, there's a user vector, and there's weighing, knowing which one you may like better or worse. And there's quite a bit that actually happens in that process. So now I actually run that process. I like to actually log in and do it because that makes it a bit more fun. So the first thing I have to do is to remove my files. That's already there. So I'm going to remove RMR. This is very dangerous, so we better pay attention to this. I'm going to remove output. Oops, did it do it? Oh my gosh, it did. Pound ls, pound RMR. RMR means recursively remove everything in a directory. And then I'm going to remove temp. So I just removed everything that from my previous run, which I just showed you. And I'm actually go do the run. So this is the command that you run. And you can see it's really not too complicated. And I want to just show you how it works. So I'm using this item-based recommendation routine. And I'm using Mahout right there. I'm just using Hadoop and Mahout. And then my input is specified as input, user file, right? And then there's the output file. You specify all those. And so now a lot of exciting things are happening on the cluster. As you can see, it's doing many, many, many MapReduce operations. So if I open the browser and go to the actual console, which I was trying to show you earlier, if I do a refresh, probably some jobs are going to start running, right? So running job, you can see that it's actually running, right? So this is the console that comes with Hadoop. So this is your normal Hadoop distribution. This is not something we modify. We don't modify the Hadoop distribution. It comes the way you know it, essentially. It will be compatible with Apache, and we also check in code monthly. Actually, I think it's daily. Check back the code, contribute the code back into the resource tree. The source tree. So as you can see, it goes on to do many different, many MapReduce operations, and it will just go on for a while. And once it's done, 13 minutes later, as you can see, it's just doing that now. 13 minutes later, it spits out that file. Magically, you have a recommendation for all your users. So I'm going to minimize that and go back to my slides real quick, since we have about 15 minutes or so left. So here are some of the algorithms that I want to just mention because they're really used quite a bit in the big data scenario. So k-means clustering, that's really important. It's really using, trying to center, trying to find different cluster within a really large data set, usually higher dimensions. So it's an algorithm that comes with your Mahout, and actually it's a relatively well-known algorithm for clustering and figuring out what group exists by just simply specifying, I want 10 groups out of this data set. Just go do it. So I can briefly describe how it works. Essentially what you're doing is you're trying to pick a center point just randomly and say, next, I want to iterate through that and figure out, how do I center that point to that, the closest set of groups. And then you kind of iterate through that and you're simply doing averages of distances with all your other points, and later on you suddenly have, when it doesn't change that much, you have 10 groups or however many groups you want. So that's really useful. Decision trees, you probably know about what that does. And naive Bayes, we do a lot of spam filters with that, right? So a lot of spam filter is done with that way. Two of the new ones is relatively interesting and new is random forest and boosting. And also there's a lot of research being done with support vector machines. It's simply answering a yes or no question with very complicated algorithms. Not really, but if you have a non-Euclidean space, it suddenly becomes much more difficult. So MIT and CMU, they're all working very hard on it. The nice thing is that it's a very scalable linear algorithm rather than something that is much higher order. So there's a lot of interesting things you can do, and of course, my favorite is PCA, principal component analysis, and ICA, independent component analysis. You can always look through them. There's plenty of resources for you to look them up. But I think I never found any really easy to understand explanations. What I might do is I actually might provide some examples for all these algorithms for you guys. So if you look, follow me on the Twitter, I guess. I just got Twitter accounts. Relatively new, trying to be more social, I guess. The fourth scenario, social media. Social media is something that I am honestly not, haven't really gotten into, but once you get into it, it's very addictive, I found. Very addictive. I'm not sure if it's a good thing or not, but I do have a huge data set, which I want to run through with you guys. So what this data set does, it's a Twitter collection that I collected over our events. Just see, what are people talking about? So who are some of the people that I should go out and meet? Who are our people that are champions? So this process is relatively easy. What you do is I'm going to just briefly describe them because all the code is available online. You can just follow them. I'm not going to run through 5 commands that takes 10 minutes each. So you use curl or Python to collect tweets. It's really simple. All you have to say, curl, Twitter account, username, password, your username, password, and you log in, and it will just keep loading. So if you keep it running for a day, 2 days, 5 days, it will collect however many you want. It will just collect. I have like 6 gigs. It's still running on the cloud somewhere. I really do have it. Seriously, I really have it still running. So I'm actually collecting that against the hashtag TEE12, and I'll show you guys a demo later. I'll put it online. That's collected about 400 megs so far, and then if you do Windows Azure, that's like another 200 megs, and then if you collect about the cloud, it turns out it has to do with the weather. So that's like 8 gigs. So there's a lot of things that you can collect. And the second thing is you want to FTP your data into Hadoop FS. So previously, as you saw, we had a little diagram that allows you to enable FTPS. So it's simply saying, okay, you can FTP your data into the actual cluster. It will reside on your HDFS. You can also copy that onto blob storage and retrieve it the way I showed you, which is ASV as an extension. So there's so many ways you can move your data these days. And then you create a table on it. And then you do your ETL. But the difficult part is that it's not a structured data set. The data set looks really funny. Let me show you. It's something called JSON. I'm pretty sure most of you know about it, but some of us don't use it on a daily basis. Let me show you how that works. So this is a typical sample data set. As you can see, it gets messy after a while, right? So there's a lot of stuff in there. Sometimes they have an item. Sometimes they don't. Sometimes they do. So you kind of have to do something more complicated with this. It comes with images. I never realized there's so much data in one tweet. It wasn't 140 characters they promised. It was more like a meg or two sometimes. So here's what I actually did. The first thing you need to do is to actually create a little table. It's called the Twitter raw, which is a very simple simple query. So I say I want to drop that table. I want to create this Twitter table, and here's my example, right? So I want to load that data. So that data is now loaded into Hive. As you can see, I actually did not say external, right? So I simply said I want to load this into HDFS. Okay. So the second piece, which is the more important piece, which you definitely want to pay attention to, which is Twitter temp. This is actually fairly complicated. So I'm creating a table, but I'm actually doing some transformation. As you can see, I created a table first, and then you want to transform that JSON raw data, which you're doing partitioning against, of course. You're just saying, I want multiple files, so on HDFS, they are distributed, right? And then I want to actually do a little bit of transformation, which is the ETL process. This actually takes a little while. Instead of just simply imposing a structure on top of something, I'm actually doing a transformation, right? So once I did that, I create a table. I actually create a table with all that information. So we're actually going to go ahead and run the query real quick. So here is let's see, the console that we have. So we actually can clear the screen. Is it COS? That's right. That seems like DOS command. That anybody remember that? COS. The thing I want to do is actually go to demo 4 and run the query for you. So there's the Twitter query. So what I'm actually doing is just simply saying I want to find anything that talks about Azure. So if you guys haven't heard more about Azure today, so there's you can see what's actually happening on the Twitter sphere. So one thing I could actually copy that, right? So copy, and I want to copy it into the. Why did it not work? Okay. What? I'm sorry. Oh, the empty lines. Okay. So, I see. I see what you're saying. So that might work better, right? Okay, let's try it. So, and I'm going to type in the second one. It's a little hard to type on this little command here. So the second one, and let's actually go run that. How's that looking? Oh, yeah, I'm sorry. Yeah, you guys are absolutely right. When I look at this from here, it's a little hard. Thank you. All right. Gotta go to the right console first, right? So let's actually take a look at this. So this will take about 2 minutes, and it's going to find all the really important Azure people. And some of them I know, some of them I don't. But now I know all of them. So this is a simple query that you can run against your Twitter data. Right? So then I can find all the famous people on Azure, and they can follow me on Twitter. Then suddenly I will have 1 million followers, right? Maybe not. But so let's just, while we're waiting for that query to run, what I want to do is I want to go back to my slides, and somebody remind me to go back to it, right? So after we finish doing that, so there's my capturing my tweet data. It's quite simple. It really is quite simple. What you can do with it. So why big data now? I think the most important is the advances in algorithms that we have, and also the fact that we have much cheaper machines. So simple things you can do, such as Jeopardy, right? So that suddenly is, we were never able to do that before. And in 1996, I think it was the IBM machine beat the chess player. So I play Go. Which is one of the games that's relatively difficult for computers because there are too many numbers. And sometimes I was always wondering if that was ever possible to make computers do better. I actually wrote some of the algorithms when I was in, I think it was second year college. It's gotten so much better that it actually can beat me now. I'm just so unhappy about that last year. So I stopped playing with it against the computers. But before, you can give it like 9-stone handicap, and it would just not even, it's just, what is this? Doesn't work. But now it can beat me with 2 stones, giving me 2 stones handicap. And I'm not a very weak player. So if you use a cluster, that is, if you use that cluster, it can actually beat me. So algorithms have really gone a lot faster, and they're mostly, a lot of them are statistics-based. So it actually uses a Monte Carlo simulation to run some of that, and suddenly, just using brute force, you can do a lot more now with computers. The same thing will happen with big data, which is simply we use brute force, divide and conquer. We buy more machines, we have more compute power, we would solve the big data problem. And the second thing is that cloud computing really helps you to solve your scalability problem. As you can see, cloud really is built for scaling, at least what they tell us, right? So there are thousands of machines up in the cloud which you can use and you just simply pay for it instead of building your own. It's really hard to build your own cluster, but you can start a cluster in the cloud. At least this is where the industry is moving towards. And I think the fact that we may or may not be able to spin up a 1 million machine cluster today is irrelevant. But the important part is that the fact that you can, the abstraction, the idea of cloud computing will take you there eventually. So we questioned if internet was going to work when we had a 2400 baud modem. But look, nobody questions whether internet was successful anymore, right? Because it worked. I think if the industry puts enough resources behind it, big data will actually succeed, and big data will do very well. There's a lot more unknowns, or sometimes we call them unknown unknowns, as Rumsfeld says, that we would be able to discover. And also collective intelligence. There's just so much you can do to mine the existing data that you collect. And I really want to offer the encouragement that there's a lot of opportunities. There's so much opportunities for you to ask the right questions even. Sometimes it's really hard to find the right question, but that's through practice. If you play with your data set, you become very good at asking questions. Sometimes a business idea and sometimes a company. And a large company is started by somebody simply asking a question and be able to use that data set and be able to be more ahead of the games, right? And finally, not only, it's really not only applied to internet, finding human behaviors. It's Internet of Things. I see a tremendous amount of opportunities for devices. There's so much devices out there, and we're going to build so much more that are they're automated, that you keep them around your houses, around companies, buildings, or even in the mountains, mining environment, that you can definitely use that to automate a lot of the, help us better understand what our environment is like in the near future. So there's just so much you can do. And what should you know now? I think it's really critical that you understand that if you have data, they're really important, and maybe they have values that you don't understand today, but tomorrow or 3 months down the road, when you hire a data scientist, or maybe you suddenly got that idea, you would be able to use that data set. And also using economics and common sense. Don't believe all those hype in the industry, but having more understanding of what big data is would really be able to help you to do more. And of course, learn to take advantage of these advanced technologies. Don't just get started right now, and really, start experimenting is a lot better than being left behind, right? So I have a lot of samples, and all this stuff is you can take a picture of it or whatever you want and download the slides. There's a lot more samples that I would like to do. I actually have really cool big samples with really big data that I want to show people, but I'm just I don't have it today because today is an introduction section. And I actually do want to go back to the original example we did, which these are all the people that showed up in my Twitter. So obviously he's not really a person, but so all these guys that showed up here are people that tweeted a lot. So maybe some of you know these guys. These guys, yes, no. Oh, you do? Okay. Well, great. So there you go. So there's my session, and thank you all very much for showing up at 8:30 in the morning. And I look forward to come back to Europe for the very second time. So this is my very first time in Europe. I really, really enjoyed it, and please fill out the evaluation and invite me back next year. Thank you very much.